Okay, here's warm-up 10R. So Elmo has 6 shirts, 5 pairs of pants, and 3 hats. How many unique outfits does he have? Let's assume he's going to use 1 shirt, 1 pair of pants, and 1 hat. That's his outfit. Okay. So we can use the fundamental counting principle here because we have 3 different categories that 1 item from each category is going to get picked. So I can just think, okay, for shirts there's 6 options, pants there are 5 options, and hats there are 3 options. And we can just multiply the number of options in each category together. And that means, let's see, we'll have 30 times 3, that's going to be 90 unique outfits that Elmo has to choose from. Okay. Next up, find the probability that Ernie randomly selects a jack and then a queen from a standard 52 card deck without replacement. So that means, okay, so we're doing a probability of jack and then a queen. So that phrase without replacement is key. So we're going to find first just the probability of pulling a jack, and then when we have multiple events, we're going to multiply by the second event. But since we haven't replaced the jack, we're going to find the probability of pulling a king, assuming that a jack has been removed from the deck. Okay, so there are 4 jacks in the deck, 1 of each suit. And there are also 4 kings, so on the second draw there would still be 4 kings in the deck, but there would only be 51 cards left. Okay, and then I multiply straight across. So let's see, that's going to be 16 over 2,652, and then we'll reduce. I could have reduced that fraction first, but I forgot. It doesn't matter, I can do it now. Okay, so that's going to be 4 out of 663 probability. Okay, all right. Next up, same problem, except this time this is with replacement. So probability of pulling a jack and then a king. So we start in the same way, find the probability of pulling a jack, but then we're going to find the probability of pulling a king, and we've replaced the jack, so it still would be a complete deck on the second draw. So 4 out of the 52 cards are jacks, and 4 out of the 52 cards are kings. There would still be 52 cards in there, right? So that's the difference with replacement. And then I'm going to reduce these first this time before I multiply. And then I multiply straight across, and I'm going to get 1 over 169. Okay. Let's now find the probability that Bert randomly draws 1 card that is a jack or a queen. So this is different than these ones, because these ones we're drawing 2 cards, one after another. Here we have just 1 card being drawn, and then, but I've got multiple favorable categories. Okay. So when we've got that word or, then we just have 1 event and with multiple categories, multiple favorable outcomes. So on these ones, I'm just going to add these probabilities together so that that I've got multiple favorable groups. Okay, so there's 4 jacks in the group, 4 out of the 52. There's also 4 queens. And I already have a common denominator, so I could add them now, but they both reduce in the same way because they're the same fraction. So I'll reduce them now, and then that's going to give me 2 out of 13. Okay. Now, in this problem, there's no overlap group between my 2 favorable categories. There's no card that's a jack and a queen. But on this next one, there is an overlap group. So we're still drawing 1 card, and this time we have a jack or a red card. Okay, so I'm going to find the probability of pulling a jack. I'm going to add that to the probability of pulling a red card, but I don't want to double count the red jacks. There are 2 red jacks in the deck. There's a jack of hearts and a jack of diamonds. So I'm going to subtract out the probability that both of those things are going to happen on the same card, both of the favorable categories. Okay, so I've got 4 out of the 52 cards are jacks. Half of the cards, I'm just going to leave it out of 52, just so I have a common denominator, but 26 out of the 52 cards are red cards. But then I've got 2 cards that are red jacks, right? So I don't want to double count them, so I'll counteract that by subtracting out like that. So on top, 4 plus 26 is 30, and subtract 2 from that, and then I have 28 out of the 52. And let's see, that'd be 14 over 26, which would be 7 over 13 if it's reduced all the way. Okay. All right, next up, Big Bird has a 38% free throw average, so he makes 38% of his shots. So we can use Pascal's triangle here to figure out the probability that he's going to hit 3 of his next 6 shots, or at least 5 of his next 6 shots. So what I want to do is set up a little chart. Okay. I'm going to do a binomial distribution here. Okay, and it's a lot like expanding a binomial. So when you have a situation where there's only 2 possible outcomes, each shot he takes, he can make it or miss. So there's only 2 possible outcomes, like flipping a coin would be another example. Okay, so what I want to do is first look at how many shots he's taking. He's taking 6 shots, so that tells me I'm going to use row 6. Okay, so in this top row of my chart, I'm going to put those numbers, 1, 6, 15. I always have trouble spacing these out. Let's see if I can make them all fit nicely. Okay, that's really the only part of Pascal's triangle that I need there. Okay, and then so what I'm going to be doing is expanding this binomial, s plus f to the 6th. Okay, that's an s, not a 5. So this is supposed to be for successes or failures. You could do miss or make, but they're both m's, so that's why I use s and f. I'm going to put my a of this binomial group is s. So I'm going to put s all the way across here, and my b term is f. I'm putting f all the way across here. Okay, and then I need to fill out some exponents in the a and b rows. So I'm going to start with this first s here. I'm going to be raising that to the 6th because I'm using row 6 in the chart, right? And my binomial is getting raised to the 6th. And I'm going to work my way down from there. So I'm going to count down to 0. So 6, 5, 4, 3, 2, 1, 0. And then for the failures, I'm going to count in the opposite direction. I'm going to start with 0. So my exponent should always add up to 6. So I'm going 0, 1, those add up to 6, and so forth. 2, 3, 4, 5, 6. Okay, and when you're filling these out, if you don't end up at 0 on that first row, then you probably used the wrong row of Pascal's triangle. Okay, all right, so let's use this chart now. So I'm going to go to this problem and say, it says, what's the probability that it makes exactly 3 of his next 6 shots? So I don't need to actually write out the whole polynomial that I would get here. I just need the relevant part. 3 of his next shots, that means we're going to have 3 successes, 3 failures. So this is the piece that I need on this problem. Okay, so that term would look like this. Okay, now what I'm going to do is put the success ratio in for S. So 38%, my success ratio is 38%, but I want to write that as a decimal. That would be 0.38. And then failure rate, I got to figure that out. Well, if he's successful 38% of the time, then that means the other, I'm going to take 100 minus 38, that gives me 62. Means 62% of the time is going to be a failure. Okay, and there's both of those rates as decimals. So now I'm going to substitute in the decimal version. So success rate is 0.38. And that's raised to the 3rd. And then my failure rate is 0.62, and I'm going to raise that to the 3rd as well. Okay? And now I can get out my calculator, multiply that all together, and I'll have the probability. It'll be as a decimal, but it'll be the probability that he makes 3 of his next shots. So let's see, 20 times 0.38 to the 3rd times 0.62 to the 3rd. Okay, and I got 0.26155. Something that, like that. And I would usually write that as a percentage, so I'd move, that's going to be about 26%. So I'm going to move the decimal 2 spots to the right. And there we go. Okay. All right. So now let's do the same kind of thing. What's the probability that he makes at least 5 of his next 6 shots? So for this one, 5 of his next 6 shots, here, well, he could make 5 or he could make all 6. So my favorable outcomes are going to be these two terms where he's making either 5 or 6 of his shots. So I'm going to add those two terms together. Okay, so that first term would be, if I simplified this, it's going to be, well, let me just write it out like this. My second term looks like that. So, hey, that first term is really just s to the 6th because f to the 0th is 1. Okay, and then, oh, forgot the f there. Then I'm going to plug in those success and failure ratios again. So I've got 0.38 for successes. And failure rate is 0.62. Okay, so let's see, 0.38 to the 6th. I'll just keep that in my calculator there. I'm going to add that to, let's see, 6 times 0.38 to the 5th times 0.62. Okay, and then I've got 0.0325, something like that. Okay, and then I'm going to write that as a percentage, so that'd be about 3.25%. That might seem pretty small, but you know, if he's not a very good free throw shooter, let's be honest, 38%, right? At least if he's in the NBA. So it's a pretty small chance that he's going to make that many shots if he's not very good at it. Okay. All right. That's the end of the warm-up, and I'll see you next time.